Here's the answer key for the review for the quiz on electron configuration. First question, what is wrong with this orbital diagram? So there's obviously the three rules that you have to keep in mind. One is that you always fill from the bottom up. So the lowest orbitals get filled first, and you never move to a higher orbital unless the ones below it are full. So in this case, we have the 1s has 2 electrons, the 2s has 2 electrons, so we've moved up to the 2p. So we haven't violated that rule in that if we, for example, had an electron up here on the 3s, well, that would be a violation because the 2p isn't full. But being on the 2p isn't a violation by itself because the 1s and the 2s are already full, so we had no other choice. Rule number 2 says that if the electrons don't have to share an orbital, they will not. So this is where we have a bit of an issue here because these two electrons are in the same orbital, even though there are other orbitals available on the same sublevel, the 2p sublevel. So the answer here is that the electron should be in separate orbitals. Okay, that's called Hund's rule. It's the second rule of the electron configuration. The only other things that could be wrong would be, for example, if there was the wrong number of electrons, right? Let's say we had 8 for carbon instead of 6, or if we had 2 electrons in the same orbital and they were both pointing in the same direction. That's that third rule that says if they are in the same orbital, they have to have opposite spins, which all of these do. It's just that these two up here shouldn't be together in the first place. So that's the answer there. Okay, what element does this electron orbital diagram belong to? I should have given you a periodic table on this one. So I'm going to flip over to the next slide, which has the table on it in a second. But in order to identify the diagram, if we assume it's a neutral atom, which you can, because we're not going to do ions just yet, we'll get to that later, all you have to do is count up the number of electrons. There's 1, 2, 3, 4, 5, 6, 7, 8. Okay, we're not being asked to figure out if this is correct or not. It happens to be correct. But all you need to know is that there are 8 electrons. So let's take a look at the periodic table. What is element number 8? Well, it's oxygen right there. So 8 electrons means element number 8, which is oxygen. That's all you have to do here. For the next question, and actually for most of these next couple of questions, it's going to be a similar process. What atom matches this electron configuration? Well, how many electrons are there? And to figure that out, if you're given the configuration written out this way, all you do is you look at the little numbers up top and you add them together. So we've got 2, 4, 6 is 10. There's a total of 12 electrons there. So what element is number 12? Down here, element number 12 is magnesium. That's all there is to it there. Okay, and which matches this electron configuration. Okay, it's a longer configuration. We get all the way up to the 3D sublevel, but the process for identifying the atom is the same. Again, we're assuming that no electrons have been gained or lost. That would be creating an ion, which we haven't done yet. So all you really need to do is count up the superscripts, the little numbers up top. 2, 4, plus 6 is 10, 12, 18, that makes 20, plus 10 makes 30. So which element is number 30? That would be zinc right here. And I'm also just going to point out, if you watch the video on the with the electron configurations from, I believe it was Thursday or Friday, they talked about the fact that the periodic table is actually broken up into blocks. This center section here is called the D block. Every atom in that group will end with a D configuration. And this happens to be the 10th element in the D block, which is why it has a 3D10. Okay, so that's just, if we, when we talk about the periodic table, I'll show you how to really even just look at this and know which element it is without having to add up all the other electrons. But so the answer here was zinc. Which of these is the electron configuration for oxygen? Well, we saw the orbital diagram, and we know that oxygen has 8 electrons. So that's the first thing, is which one of these has 8 electrons? Well, really the only one here, that's 16, that's 10, this is more than that. The only one that has 8 electrons is this one here. The only other thing you need to know, there needs to be 2 things that are correct. One, it has to have the right number of electrons. And since none of the other ones had 8 electrons, process of elimination tells you right away that this has to be the choice. But if there were more than one that had the same number of electrons, you would then have to look at, okay, do they go in the right order? And are they filled up correctly according to the rule, where you don't have partially filled orbitals and then orbitals above them that have electrons? So that would be the other question that I could give you, is if I gave you 2 choices that both had 8, but one of them was in the wrong order or violated one of the rules, that would be the way to eliminate that choice. Actually, I think this is going to be the case here. So which of these is a sulfur atom? So where is sulfur? It's actually right below oxygen on the periodic table. It has 16 electrons. So this is 2, 4, 10, 16. So this is a possibility because it has 16. 2, 4, 10, 12, 18. So we can eliminate that one because it's got the wrong number. This is 2, 4, 10, 12, 16. So that's a possibility. And then 2, 4, 6, 12, 16. All right, so we could only eliminate one that had the wrong number of electrons. So now we need to figure out which one of these is in the correct order and doesn't violate any of the rules. So here's the order down here. So we can start by looking at that. 1s, 2s, 2p, 3s, 3p. Well, this is 1s, 2s, 2p, 3p. That skips the 3s orbital, so we can eliminate that one. This one is 1s, 2s, 2p, 3s, 3p. So that's the right order. So we're zeroing in on this being a possibility. This one is 1s, 2s, 3s. Well, that switches these two, which makes it the wrong order. So the only one that is in the correct order, so this one, just to highlight it here, this one has all of the correct numbers in all the correct letters, and it has the right number of electrons, but it's not written in the correct order. So that's why that one is wrong. The only difference between that one and this one is that the 3s and the 2p are reversed. Okay, so just keep that in mind. It has to follow this sequence down here. Okay, how many electrons can each orbital hold? Now, a few people were asking about this when you were going over the practice problems. When you think about an orbital, and people say, well, you're talking about the s orbital, it's a distinction. Okay, orbital is an area where electrons can exist. When we do the diagrams, a box is an orbital. Sublevels are the different letters. So the different sublevels have different numbers of orbitals. S sublevels have 1 orbital. P sublevels have 3 orbitals. Each orbital can hold 2 electrons. Sublevels can hold more than 2 because they might have more than 1 orbital. So again, it's like the orbitals are the rooms, and then the letters are the different types of apartments or rooms and suites in the hotel. You've got a studio apartment with only 1 room, can hold 2 electrons. Well, the premium here has 3 rooms. Each room can still only hold 2 electrons. Okay, that's the most important thing to remember here. Orbital means 2 electrons. Sublevels, which is what the letters represent, can have more than 1 orbital. That's how you get multiple different electrons. And then the big numbers here are the energy levels. Each energy level is made of different sublevels. Different sublevels are made of different orbitals. So it kind of breaks it down that way. orbitals. You can have multiple orbitals that make a sublevel and multiple sublevels that make an energy level. So to answer the second question, how many electrons can the 2p sublevel hold? Well, when it's talking about how many electrons they can hold, it really doesn't matter that it's 2p. What matters is that it's a p sublevel. It could be 2 or 3 or 4p, doesn't matter. The p sublevels have 3 orbitals. Each orbital can hold 2 electrons, so the 2p sublevel could hold 6 electrons. So could the 3p sublevel or the 4p sublevel. So don't be fooled by the fact that it says 2p or 3p or 4. It's the letter p is what tells you how many electrons it can hold. So having said that, how many electrons can the 7s sublevel hold? Again, the 7 is irrelevant in terms of how many electrons it can hold. S sublevels, we said on the last slide, every single time you see the letter S in a configuration, that means it has one orbital. One orbital can hold 2 electrons. And then this configuration, we're not being asked to determine if it's correct or not. It is. We're actually not even being able to identify what element it is, although we could if we had a periodic table to look at. All we want to know is how many electrons does this atom have? The electrons are the little numbers up top called superscripts. So 2, 4, 6 is 10, 12, 18, 19. That atom has 19 electrons. If we wanted to look it up, we'd see that it's element number 19, which is potassium. Okay, draw the orbital diagram for calcium, which has 20 electrons. Okay, so we need 20 electrons. The orbital diagram means arrows. Okay, so we've got the boxes, the orbitals. Remember, each one of these orbitals can hold 2 electrons. We just have to follow the rules. So starting at the bottom, 1s. 1 electron, 2 electrons. 3 electrons, 4 electrons. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so again, the common mistake that people might make is if you went and put the 4s and then put 1 up here on 3D, you wouldn't do that just because there's room on the 4s to put that 20th electron, so don't go higher than you have to. Really, in this case, because all the orbitals are full, so the only other mistake that you're likely to make is to put 2 arrows in the same direction in the same box. Just make sure they're pointing in opposite directions when they're together. Or just miscounting and having the wrong number. If I didn't give you the boxes, obviously there's a possibility you could put the boxes in the wrong order, but that's not going to be the case here. Okay, draw the diagram for neon with 10 electrons. Same process here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I'm done. All the boxes are full. Arrows pointing in opposite directions, and I didn't go any higher up onto the scale than I had to. So that tells me that I've done the diagram correctly. All right, writing the configuration for iron with its 26 electrons. When you're writing these configurations, giving you the sequence up here of how they go. So all you have to remember, or what you need to remember, is how many electrons can fit in each sublevel. S can always hold 2. And then it goes 2s, 2. Next is 2p. P sublevels can have 6. And then 3s, 2. 3p, 6. 4s, 2. And then it's 3d, 6. Okay. The D can hold up to 10. So S can have 2. P can have 6. D can have up to 10. F, if we ever needed to use that, can hold up to 14. Okay. The orbitals don't have to be filled, but these are the maximums that they can hold. Once you get to these numbers, you have to move to the next orbital. But you can have less than that if and only if you're on your last sublevel. So the last sublevel can be incomplete. All of the ones before it must be full in order for it to be correct. Okay, so I couldn't, for example, have 3p4 and then 4s2 and so on, because that would mean I moved to the 4s before the 3p was full. So that's the key thing to keep in mind here. Okay, just a couple more of these. Fluorine with 9 electrons, 1s, 2, 2s, 2, 2p. Well, let's see, we've got 2, 4. To get to 9, I need 5. So the p could hold up to 6, but I didn't need to fill it up. I filled the ones before it, but the last one is the only one that can be incomplete, and it's okay if it is, as long as you have the right number, right? This adds up to 9 across the top, and only the last one is incomplete, so that's fine. Okay, and then finally phosphorus with 15 electrons, so 1s2, 2s2, that's 4, 2p6 is 10, 3s2 is 12, and 15, we're up to 3p. Right, so I'm just following along this order. We get to 3p. I'm at 12. I need 15, so I only need 3 more electrons here. Add up the numbers on the top. They add up to 15. Okay, that's number 1. Number 2, I went in the correct order according to this list. And number 3, the only orbital that's not full is the last one. And that's only because I needed 3 more, even though it could hold 6. Okay, so you can't go over 2 for an S. You can't go over 6 for a P. You can't go over 10 for a D or 14 for an F. But if you get to that last sublevel and you don't need 6 in the P orbital, don't put 6 because that's the wrong number. Okay, then your number would add up to 18, which is not what you want. All right, so keep going along, fill them up as you go until the numbers across the top add up to the number of your element. And that's all there is to that. Okay, I'll give you the sequence. I'll give you the periodic tables where you need them. I'll give you the boxes for the orbital diagrams. You have to remember how many electrons can go in each orbital, how many orbitals there are on each sublevel, so you know how many electrons to go for the S, P, D, and possibly F, but I am not likely to make you do any F sublevels. But again, if I'm giving you the order and telling you how many can go in each one, you should be able to go as far as you need to, all the way up to 7p. Just fill them in until you get to the right number. But I'm not likely to get past, if I even got to 4d or 5p, because then we get into the F's above that. But that's probably as far as I'll make you go or ask you to go. All right, so there you go.